Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett and we cover all things Gen Chem related on this channel. In this video, I'm going to be covering ionic equations and net ionic equations and how they differ. Let's get started. In a previous video, we learned about precipitation reactions, and those are the reactions that when they create these products, one of the products ends up being insoluble in water. So as a result, we end up seeing something new being formed and can indeed say that a reaction has occurred. And so the reactions that we were writing in those precipitation reactions are what we call the molecular equations. And the molecular equations are just simply describing all the compounds that are involved in the products that are produced. Now, the ionic equation, and something we're going to learn about, the net ionic equation, help us to understand what's the true driving force of these reactions. What's getting this reaction to occur? What's creating that something new that we see? And so if we look at this example here, we have potassium hydroxide with magnesium nitrate reacting to form potassium nitrate and magnesium hydroxide. We can predict those things based on swapping those partners, swapping those ions, and creating something new. And so the ionic equation is going to help us to understand what ions would be present in the solution as this reaction occurs. And so how you go from your molecular equation to your ionic equation is by simply ionizing anything that you've written on the reactant side or the product side that has the designation of aqueous. Because again, aqueous means it's dissolved in water, it's soluble, so the ions would be present. Anything that is insoluble or that has that solid, liquid, or gas designation, you would keep it together. You don't ionize it because it's not floating around as independent ions. And so the ionic equation, your insoluble material will stay or remain in its whole molecule form or whole compound form. And so if we take the equation from above, we would ionize or dissociate my potassium hydroxide. And notice that because it was a 2 in front of there in the coefficient position, I'm creating 2 potassium ions and 2 hydroxide ions as that ionizes. Same thing with the magnesium nitrate. I'm getting my magnesium ion and 2 nitrate ions. On the product side, when I look at it, I get my potassium ions, 2 of them, and 2 nitrates being formed. But now notice we keep this entire compound together. And that's because it is insoluble in water. It's not going to ionize in this solution, okay? And so when you're writing ionic equation, anything that has AQ after it, and again, you can predict if it's AQ, aqueous, using that solubility table that I showed a few videos ago. And anything that has that solid designation, we keep together. So once we've developed our ionic equations, we then want to identify what are called our spectator ions. So spectator ions are just like the name implies. They're just observing the reaction that's taking place. Just like if you go to like a baseball game, a spectator is someone that's just not playing the game, but just watching. And so your spectator ions are those ions that appear on both sides of the equation after you've done this ionization process. And so in the example that we're working through, you can see that some potassium ions are on the reactant side and the product side. So that would be considered a spectator ion. You can also see that there's nitrate ions on both sides. And so that would also be a spectator ion. So then to get the driving force, to figure out who's actually playing the game, or to determine what's called the net ionic equation, we now remove those spectator ions and we're able to develop equation, which is in this case, hydroxide ion plus your magnesium ions will create magnesium hydroxide. And so the fact that we have this net ionic equation that's occurring lets us know that indeed a chemical reaction has taken place, a chemical change has taken place. Remember, in the previous video, I had stated that if you did not have a solid, liquid, or gas formed as one of your products, you didn't have a precipitate formed, we would say no reaction. Well, the reason that is because if we had all aqueous across the board, that means all of the ions are spectators. And so we would be able to cancel them all out. So there is no net reaction that's occurring. Nothing new is truly being formed. All the ions are just still kind of floating around there. Okay, and so that's the difference. Ionic equation, we're ionizing anything that has aqueous after it, keep solid liquids or gases together, and anything that has that appears on both sides of the reaction, we remove as spectator ions, and we're able to get the net ionic equation or the driving force of these chemical reactions. And so let's practice writing ionic and net ionic equations for the following. And so we have the reaction shown. And so anything where we see aqueous, we will ionize. So the potassium sulfate, we would end up getting potassium ions out, positive charge. And how many do we have? Well, there's 2 of them. Now we're not going to put a 2 here as a subscript. Put it in the coefficient position. Plus some sulfate ions, SO4, 2 minus. Plus, now my silver nitrate will ionize. So I have silver ions, and there's 2 of them. And I have nitrate ions with a negative charge, and there's also 2. And then it's going to create potassium ions, and there's 2 of them, and nitrate ions. There's also 2 of them. And then this, because it's insoluble, we keep it together. Okay, all the ions that I wrote should say aqueous after that. I'm just being a little lazy right now because it'll get too cumbersome on my screen. But if on a test, make sure you write aqueous there. All right, so that's our ionic equation. Now our net ionic equation, we're going to be removing any spectator ions. So where's the spectator ion? Well, I see I have potassium on my reactant. I also have potassium on my product. I have nitrate on my reactant and nitrate on my product. And so those are going to get removed. And so the resulting reaction, or the net ionic equation, is sulfate with a -2 plus the silver ions, +1. And that's going to create my silver sulfate. Again, something new is being formed. Notice if you've ionized this correctly, you should end up with a balanced equation at the end. If you don't, that means somewhere along the line you made a mistake as you were ionizing. So check your coefficients. Okay, let's check this next one out. So again, anything with AQ for the ionic equation, I'm going to ionize. And so I would have sodium ions, and I have 2 of them, plus carbonate ions, and I have 1, plus hydrogen ions, and I have 2, plus chlorine ions, and I have 2 of them. Again, balancing off that coefficient, produces sodium ions and chlorine ions. And then the things that aren't aqueous, we keep those together. And so this carbon dioxide and water is the result of the carbonic acid that was produced quickly breaking down to form these 2 byproducts. And so we would say CO2 gas still remains and H2O liquid. So that would be our ionic equation. Now for the net ionic equation, we now are going to be removing those spectator ions. So where do you see a spectator ion? Well, we see we have sodium on both sides. We also have chlorine or chloride ions on both sides. And then the remaining part would be our net ionic equation. So we have that carbonate ion and the hydrogen ions. And that's what's producing our carbon dioxide gas and water. Now, a subcategory of these reactions are these acid-base reactions. And so when you have acid-base reactions, remember, acids are things that have a pH of less than 7. Bases are things with a pH of greater than 7. And so when we react these together, this is known as a neutralization process. We're neutralizing, coming closer to that pH of 7. And so in an acid-base reaction, the product that you're always going to expect is some salt being created and some amount of water. Because when we swap that hydrogen with whatever the cation is in the base, we end up with hydrogen and hydroxide coming together to form water, which is a liquid. And then that salt that's coming together, in this case, calcium and nitrate, which ends up being normally an aqueous product. And so when you look at whatever the net ionic equation is for any acid-base reaction, you should end up with the hydrogen ion reacting with the hydroxide ion. And again, those two things help us to predict things like pH and POH, which you'll learn in later chapters. And then they produce our liquid water. And so typically that salt is going to be a soluble material. And so your water is going to be that something new that's being formed that's creating this reaction that's occurring. So just some background about acids and bases in solution. Remember, acids are things that can ionize and form those hydrogen ions in solution. And really what they're going to be creating as they're donating that hydrogen to the water molecule is something known as hydronium ions or H3O plus ions. And a lot of people use hydrogen ion and hydronium ion interchangeably. And bases are things that dissociate in water to form hydroxide ions. So like ammonium, although it doesn't contain hydroxide ion, it takes that hydrogen off of the water and it creates a hydroxide molecule that can be present. And so in a reaction of an acid with a base, the hydrogen from the acid combines with the hydroxide from the base to make water. And then the cation and the anion are going to come together and form a new salt. And so your overall formula would be acid plus base is going to create a salt in water. So just shown for you here is a few examples of some common acids, and you can see them listed as being either strong, moderate, or weak, and that's based off of will they fully ionize or only partially ionize. Strong acids can fully ionize, weaker acids only partially ionize. Okay, and this is just more FYI knowledge. And then also some other common bases that are shown here with the same premise behind them. And so if we look at the reaction shown here, where we have hydrochloric acid and sodium hydroxide reacting, again, two aqueous solutions. When we combine them together, what we're creating, the something new we're creating is we're releasing that water and then also creating this soluble sodium chloride, this salt material. And so we can put all of this together and actually predict and write a molecular formula, an ionic formula, and a net ionic equation for these acid-base reactions. So if we had something like nitric acid, and again, you got to know how to name these things and how to get the formulas. So nitric acid would be HNO3, and it's aqueous. It's telling us it's aqueous, is reacting with calcium hydroxide. So that would be calcium and hydroxide coming together. Calcium we know is +2, hydroxide is -1, so we would need that 2 subscript. And then we're going to swap your partner, swap the ions. So you end up with calcium and nitrate coming together. Remember, calcium keeps that +2, nitrate -1, cross it down, we get the subscript. And we get hydrogen and hydroxide coming together, or H2O, and we don't need any subscripts. We do need to balance this equation, and so we could put a 2 over here with the nitric acid and a 2 with the water. We would then check our solubility charts, and we see that calcium nitrate is also aqueous. And the HOH is really H2O, which is a liquid. The reason why we're not writing aqueous behind water is because water is a pure substance. So there's not something else dissolved in it. It's just water. So that's why we write liquid and not aqueous. Okay, keep that in mind. Okay, so that represents our molecular equation. Now to get the ionic equation, we then are going to ionize anything that has aqueous behind it. So the nitric acid will ionize. So we get 2 hydrogen ions and 2 nitrate ions. The calcium hydroxide will also ionize. So we get calcium ions and now 2 hydroxide ions coming out. Calcium nitrate will ionize. So we get calcium and 2 nitrates. And then we will get keep our water together. And you can rewrite that as H2O if you like. Either one is fine. And that stays together. Remember, we only ionize things that have aqueous after them. And then to get to the net ionic equation, we now are going to remove any spectator ions. So our spectator ions in this case would be our nitrate, which appears on both sides, and calcium, which also appears on both sides. And so the resulting equation is 2 hydrogens plus 2 hydroxides is giving me 2 of my waters, HOH or H2O. And we can reduce that down, write it in its simplest whole number ratio. So we would get H plus OH minus creates water. And we would anticipate this net ionic equation for any acid and base reaction. All right, let's try 2 more examples predicting the products and then coming up with those net ionic equations. And so here we would have HCl and barium hydroxide. So we have barium chloride being created with the 2 behind the chlorine because of barium's 2 charge, and HOH or water. We know water gets the liquid designation. Barium chloride is going to be aqueous. We can then ionize to get our ionic equation. So hydrogen. Oh, before we do that, let's make sure we balance the equation. So put a 2 here and a 2 here in the coefficients. Now, when we're ionizing, we adjust the number of ions accordingly. Okay, barium hydroxide will ionize. It has that aqueous after it. And then we're going to create barium ions on this side and chlorine ions. We got 2 of them. And then we keep that water whole, keep it together, because it does not have that aqueous designation. We then remove our spectator ions, which in this case would be your chlorine ions and your barium ions. The result is 2 hydrogens plus 2 hydroxides produces my water. And we again can reduce this down to hydrogen plus hydroxide creates water. Okay. All right, last but not least, we have H2SO4 or sulfuric acid and strontium hydroxide reacting with one another. Again, swap those cations. So we have strontium and sulfate coming together. And again, remember, whatever charge it was in the reactant, it'll be that charge in the product. So this is 2 minus, 2 negative, so we don't need any subscripts, plus our hydroxide and hydrogen coming together to form that H2O or HOH, either way you write it is fine. We do need to balance it, so we would need a 2 here, and that should balance us out. And then we know that this will end up being a liquid, and the strontium sulfate, that should be aqueous for us. And so we then go through and ionize. So we would have 2 hydrogen ions and a sulfate ion created, plus a strontium ion and 2 hydroxide ions. And that produces strontium ion and sulfate ions. And then we keep our water together. Now to get to the net ionic equation, we now remove our spectator ions. So that means I can remove my sulfate ion and the strontium. The end result looks exactly the same as what's above. And so we end up with our hydrogen ions and our hydroxide ions that are creating something new, creating that water. And we can reduce down the formula. And so we end up with H plus OH minus creates our water. I hope this video helped you understand how to actually predict net ionic equations and ionic equations, and how this is applied to not only these ionic reactions, but also acid-base reactions. Make sure you guys like, comment, and subscribe, and let me know what kind of content you want to see in future videos. I'll see you guys later. Have a great day. Bye-bye.